This is a transformer. It's the T in ChatGPT, and it's the architecture of all modern AI language models. There are many different parts to a transformer, but the core idea and the innovation is the self-attention mechanism. And the focus of this video is going to be just on that, just on attention. In this video, I want to try and create a simple visualization for why we need attention and what it actually does. This video is not about the mathematics of it, and it's not about creating simple analogies. It's about visualizing with animation the actual steps of the algorithm. Up until 2017, where Google released the paper "Attention is all you need," no one was able to create an AI model that really understands language. And even the most cutting-edge chatbots really didn't make a lot of sense. And that's because it's really hard to understand language. But you might ask yourself, it's also really hard to understand images, and AI models back then already were pretty good at understanding images. So before we start, let's just talk for 1 minute about what's so special about the structure of text that make it so hard to train AI models on. And there's actually one simple answer for why it's so hard to understand text. Any word and any part of a word in text can influence the meaning of all other words, even if they are very far apart. If you read a book, it's not hard to imagine how changing one paragraph in the first chapter can influence the whole story, and changing the meaning of text that will happen 100 pages later. And this is not special for stories. Any text has what we call long context dependencies. And the problem is that we don't know what parts should influence what other parts in the text. And that's exactly what attention is for. It's for understanding what parts relate to other parts and in what way. So now that we already talked about why text is so hard for models to understand and what attention aims to do to help them understand it, let's talk about the actual implementation of the self-attention algorithm. So let's start from the beginning and recap some things you probably already know. To input text to our model, we first need to tokenize it, which means to split it into small chunks and represent each chunk as a list of numbers. Each one of those number lists is called a token embedding. For now, you can think of those numbers as arbitrary, unique numbers that are used to represent every token. And you probably noticed I gave each one a different color. Because from now on, we'll ask questions like how similar is one of those list of numbers to another. And because they are very high dimensional, they have a lot of numbers, it's very hard to wrap our head around it. So let's give ourselves an easier time and represent each one with a different color, where similar vectors have similar colors. And embeddings that are farther from each other have a more different color. Let's take, for example, the token the. If you remember from earlier, every token is represented by a list of numbers. And those lists of numbers are represented in this example as a color. So this little purple square represents the vector that represents the token the. In the attention mechanism, we take every token and pass it through 3 networks. Those networks are typically very small and simple, and we use them to produce 3 values: Q, K, and V. Or by their full name, query, key, and value. And later in the video, it will become much more apparent why they are called with those names and how those names relate to how we actually use those values. If we take a sentence like "the dog is sleeping" and pass each token through those 3 networks, we will get the values for each token. And you can notice that every token produces a different set of K, Q, and V. And now we're ready to run self-attention on this sentence. Let's again focus on the token the. And specifically, let's look at the Q value of the. I remind you that Q means the query of that. And the reason it's called a query is because this value is used to search for other related tokens. And the way we're doing this search is by comparing the current word query with the key of all other words. You can think of the query as the thing we used to search for other related words, and the key of those other related words as the thing that we match with the query to understand if there is a relation. In this example, you can see that the Q of the and the K of dog are very similar in color, which means that they are very similar in numbers. And that's where value comes in. V is how we are going to influence the current word in case there is a match. And because the key of dog and the query of the are similar, we will take the influence of the value of dog. And if it's less similar, like the Q of the and the K of is, we will still take the V, just a much weaker version of it. Then just do the same for the last word, and then we have the new value of the. And all we need to do to get the new value is combine all the values that we added up with their different strengths. And now that we did it for the token the, we just need to do it for the rest of the tokens. So now if we focus on the token dog, we can take the Q of dog and compare it with the key of the. And since Q and K are not similar to each other, the V of the is going to have a low influence on dog. So when we train the networks that produce Q, K, and V, we want to train the networks that produce Q and K to produce similar colors for tokens that are relevant for each other, and more different colors for tokens that are more different. And we want V to provide us with the context of how the current token should influence other tokens. So to recap, after creating the query, key, and value vectors using our networks, we will take the query of every token, and to get the next value of that token, we'll add to that token the value of every other token, but with a strength proportional to the similarity between the current query and the other's key. Or, if you're confused about this code, it's just the same thing we showed in the animation. At this point, this whole algorithm might feel a little bit arbitrary. So I want to take a step back and go back to the start and reconsider what is the problem that we're trying to solve, and see if this arbitrary method can help with that. So if you remember, the problem with text is that different parts of text can influence each other, and we don't know which parts are relevant to what other parts and in what way. And by introducing this attention mechanism somewhere in our network, we allow the network to learn just that. The similarities between queries and keys will allow the network to learn what parts are relevant to what other parts, and the value will help the network to learn in what way they are relevant. To get an even stronger intuition of how attention mechanism works, I'd recommend getting some hands-on experience solving problems related to attention. And for that, I'm very proud to introduce you guys to the sponsor of this video, Brilliant. Brilliant is an online learning platform that helps you get smarter every day, with thousands of interactive lessons in math, science, programming, data analysis, and AI. And unlike just watching video lectures, Brilliant allows you to solve hands-on problems, which is much more effective for learning. It trains you to build hands-on problem-solving skills and make learning your daily habit. No matter where you are, you can learn on the go with Brilliant. You can even learn directly about topics discussed in this video right inside Brilliant and become a smarter, more capable AI engineer. So go to brilliant.org/gallahat to get your 30-day trial, and if you come from my link, you even get 20% off on the annual subscription. Let's get back to the video. So now we have this architecture that is able to learn what parts are relevant to other parts and in what way. So we are done, right? But wait, everything we talked about should not be possible, because no step of the algorithm I described so far considered the order of the words. The current implementation of attention that I described would see a mix of words and a coherent sentence using those words as the same thing. And it would have no way to differentiate between a sentence like "a man fell overboard" and "a board fell over man." So the question is, how can we make our attention algorithm be aware of the position of each word? And that's where positional encodings come in. Positional encodings allow the attention to consider the position of each token when determining the query, key, and value. When creating the token embeddings, we can just add a few dimensions to each token that has some relation to the position of that token. But what numbers should we put in those dimensions to help the network understand the position of each token? The naive approach is just to add another dimension to each token that goes from 0 in the first token to 1 in the last. And while this will work, there is a much better way to do it. And it turns out sine waves are the best way to do it. But just one sine wave has the same problem as the naive approach we tried before, as it's too smooth and too one-dimensional. And it's also symmetrical, so the network would see the reverse of the sentence as the same thing as the sentence itself. The solution is to add many sine waves with different frequencies as different dimensions for each token. Doing it with sine waves in different frequencies would allow the network to learn relationships like every 2 tokens or every 3 tokens, or next token or previous token, because it has much more context in regards to the position. Now, if you want to build a large language model, you wouldn't use just one attention layer. You would need to capture a lot more kinds of relationships and more abstract ones. So often in real-world models, we see models that use a lot of attention layers, one after another or aside each other, to capture much richer relationships between the tokens. I hope that next time that you hear the phrase self-attention, you would have a stronger intuition to what's going on behind the scenes and why it's useful. And I hope you'll keep following the curiosity that got you to this video, and I'll see you in the next one. Bye bye.